Section 7.7, Inverse Relations and Functions. Let's look at a definition. If a relation pairs an element A from its domain, and we know a domain are the x values of the relation, to an element of B in its range, which we know are the y values, the inverse relation pairs B with A. In other words, if my relation is the ordered pair A, B, where A is from my domain, B is from the range, is an ordered pair of the relation, then the inverse is BA. In other words, the domain becomes the range becomes the domain. In other words, you switch the x and y values. Here's a mapping to demonstrate this. Here's our domain of the relation, 2, 5, and 9. Here's the range, 3 and 5. And we see the ordered pairs, or the mapping, 2, 3, 5, 5, and 9, 5. If we want the inverse of that, that would then switch the domain to the range, and the range becomes the domain. And our ordered pairs, our mapping goes 3, 2, 5, 5, and 5, 9. Again, the range of the relation is the domain of the inverse, and the domain of the relation is the range of the inverse. On our next slides, we want to find the inverse of the given relation, graph the given relation, and its inverse. And we'll also keep looking at domain and ranges of our relations and inverses. Let's look at our first example. Here, I have a relation on a table form, and I have the domain and range identified. I want to plot that. I'm going to use a calculator, so I make a list 1 of my domain and list 2 of my range, and I'll graph that relation. Now let's take a look at the inverse. I have the domain, which was the previous relation's range, and I have the range, which was the previous relation's domain. We want to set up a list in my calculator of those values, my new domain, my new range, and I want to graph that. And you can see I have my original relation and my inverse of that relation. Interestingly, if I plot the identity function, which is y equals x, on the same coordinate plane, I can get a reflection of the relation over the identity function that is the inverse. And you can see they map exactly over my identity function. So graphically, anytime we graph the relation and its inverse on the same coordinate plane, and I also graph the identity function, the relation will be reflected over that identity function. That's a graphical representation of the inverse of that given relation. In this example, I want to find the inverse of each relation, graph the given relation and its inverse. Let's graph my original relation. Here's our domain, 0, -3, -4, -1, and our range, 3, 1, 2, -3. So I have 0, 3, 0, 1, 2, 3. I have a -3, 1. -4, 2. And -1, -3. The inverse is going to be 0 is part of the domain, becomes the range, -3, -4, -1. The entire domain becomes the range. The range becomes the domain. 3, 1, 2, -3. And let's plot those points. 3, 0. 1, -3. 2, -4. And -3, -1. And we can see that these values reflect over my identity function, visually representing an inverse of the given relation. On the previous slides, we found the inverses when I was given a table of the ordered pairs, and all I did was flip the domain and the range, and that would create my inverse. Well, what if I'm given an equation? How do I find the inverse? Well, here's the procedure. If I'm given a function f, we want to rewrite y instead of f of x. When I have that, I'll have an equation in terms of y and x. I want to interchange the x and the y's. In other words, I want the domain to become the range and the range to become the domain. Once I switch my x and y values, I want to solve for the new y. The solved equation is the inverse of the original function, and it's labeled f negative 1x and called inverse of f of x. Let's look at an example. Here I want to find the inverse of the function, and I want to determine is the inverse a function. We can see I have my identity function graph, y equals x, and here is the function that I was given, y equals a negative 2x plus 4. It is graphed. If I perform the vertical line test, it intersects my function only once. Therefore, this is a function. So let's determine what the domain is. We always like to know what that is. The domain is my x values. So my x values can be all real numbers. And that's going to represent real numbers. My range are my y values, which can be all real numbers. Let's determine the inverse of that function. I don't have to change from f of x. It already is a y. Now I'm just going to interchange my x and y values. In other words, domain becomes the range, range becomes the domain. That's going to give me x equals a negative 2y plus 4. Subtract 4 on both sides. X minus 4 equals a negative 2y. Divide by a negative 2. And y is going to equal a negative 1/2 x plus 2. I can graph by the slope-intercept form. Let's graph that. I have 0, 2 as my y-intercept. My slope, a negative 1, 2, down 1 to the right 2, down 1 to the right 2. Let's plot my inverse. Let's determine if that's a function by a vertical line test. It would intersect my red line only once at each vertical line. Therefore, this is a function. My domain of the inverse, my x values, all real numbers again, and the range of my inverse, again, all real numbers. Also, this may not look like a reflection over the identity function, but I can check with ordered pairs. Here, I have 2, 0, 0, 2. That is a reflection over my identity function. Here I have 1, 2, and I also have 2, 1. That is a reflection over my identity function. So you can see the relation and its inverse reflect over my identity function. Again, I want to find the inverse function, and I want to determine if the inverse is a function. So we have our function graphed. It is a quadratic. And what I want to do is determine the domain and range. My domain are my x values. My x values can be all real numbers. I can put any x value in here that I want, positive or negative. So therefore, it's all real numbers. My range is going to be my y values. And you can see I don't have any y values below 0. Therefore, y is greater than or equal to 0. Let's take a look at the inverse. I have to determine that by interchanging my domain and range in my function, or also interchanging my x and y. Let's take the square root of both sides. When I do, I get the square root of x. that will be plus or minus equals y plus 2. Solve for y. Subtract 2 on both sides. Y equals a negative 2 plus or minus the square root of x. Now I need to determine values for two parts, negative 2 plus the square root of x and a negative 2 minus the square root of x. If I substitute in 0 here, square root of 0 is 0, negative 2 plus 0 is a negative 2. If I plug in a 1, that's going to give me the square root of 1. Negative 2 plus 1 is going to give me a negative 1. If I plug in a 4, square root of 4 is 2, negative 2 plus 2 is 0. Here, if I plug in 0, I'm going to get 0 and a negative 2. If I plug in 1, square root of 1 is 1, but a negative 2 minus 1 is a negative 3. If I plug in 4, square root of 4 is 2. A negative 2 minus 2 is a negative 4. Now I can plot those ordered pairs. And when I do, I'm going to get 0, negative 2. I'm going to get 1, negative 1. I'm going to get a 4, 0. I get 4, negative 4. And I also have 1, negative 3. And I graph those ordered pairs. I get the quadratic laying on its side. I also can see that this is a reflection over my identity function. Now I need to determine the domain and range. My domain, my x values, are going to be to the right of the y-axis, except for the one that's on it. So I'm going to have x is greater than or equal to 0. And my range, or my y values, can be all real numbers. And I can determine if this is a function by the vertical line test. Since my vertical lines intersect my graph at more than one point, this is not a function. Our next example, I already have it graphed. Y equals a negative x squared minus 3. You can see that this is a function. I also want to determine the domain. The domain is going to be x such that my x values can be all real numbers. And my range is y such that, and my y values are all below or equal to 1, 2, negative 3. So y is less than or equal to a negative 3. To make this problem go quicker, I actually found the inverse. I switched the x and y. I added 3 to both sides, then divided by a negative 1, then took the square root of both sides, which gave me plus or minus the square root of a negative x minus 3. Remember, I need all positive values as my radicand. Therefore, I'm going to start with a negative 3. Negative 3 is a positive 3, minus 3 is 0, plus or minus 0, and negative 3 equals 0. Negative 4. Now I want values that I can actually find the perfect square root of, so I chose a negative 4. Negative is a positive 4. 4 minus 3 is 1. Square root of 1 is 1, plus or minus 1. And negative 7. Negative 7 is a positive 7. 7 minus 3 is 4. Square root of 4 is 2, plus or minus 2. Now I'm just going to fill in my ordered pairs. Negative 3, 0. Negative 4, plus and minus 1. and -7 is a positive and -2. Now I just want to bring over my graph. And we can see by our vertical line test that this is not a function. And I can determine the domain. What allowable x values do I have? That would be all values of x that are less than or equal to a -3. And my range, my y values that are allowable, is all real numbers. My next example, I have f of x equals the square root of a -x plus 4. It's drawn here in black. I have the domain. I have x values less than or equal to 1, 2, 3, 4, less than or equal to 4. My y values are y greater than or equal to 0. I then found the inverse. I converted f of x to y, then switched the x and y's. I squared both sides and got x squared equal to a -y plus 4. Subtracted 4 on both sides and got a -y equals x squared minus 4. And divided by a -1, getting a -x squared plus 4. I know that the domain and range of my new function has to be the domain and range switched on my regular function. So my domain here is going to have to be x such that x is greater than or equal to 0. And my range is y less than or equal to 4. And you can see I have a domain, x, that starts at 0 and increases. When I substitute those values in, I get values of 0, 4, 1, 3, 2, 0, 3, -5. And that makes my range decrease, y is less than or equal to 4. I can graph those points. I get 0, 4. I have 1, 3, 2, 0, and 3, -5, and have drawn that in. I now can determine that this is a function by the vertical line test. So this is a function. And I can see that it is reflected over my identity function y equals x. For my last example, I have y equals 2x minus 2 quantity squared minus 1. It's drawn in black. To graph that, I wanted to put that in vertex form so I could use my families of functions. So I broke this into a product of its linear factors and FOILed and simplified. And then what I did was complete the square. We've done this in previous sections. What I ended up with was 4 times the quantity of x minus 1 squared minus 1. That gave me a stretch, and I could find my vertex at a +1, -1, which I have here. I know that I have a stretch of 4, so I go over 1 and up 4 and over 1 and up 4, and I have that graphed. Then I know that I can find the domain of that function of x is all real numbers, and y is greater than or equal to a -1. To find the inverse, I just know that my domain is my range, so that is x is greater than or equal to a -1, and my domain becomes the range, which is all real numbers. I then switched my x and y's and found the inverse, and that equals y equals 2 plus or minus the square root of x plus 1 over 2. Keeping my domain and range in mind, I have x greater than or equal to a -1, and my range can be all real numbers. I found values to have my radicand be a perfect square. I used a -1. A -1 plus 1 is 0. The square root of 0 is 0. 2 plus or minus 0 is still 2. 2 over 2 is 1. 3 plus 1 is 4. The square root of 4 is 2. 2 plus 2 is 4 over 2 is 2. Or 2 minus 2 is 0. Divided by 2 is 0. I plotted those ordered pairs and determined that that is my graph. Now I know from the vertical line test that that is not a function. But I can see that it is reflected over my identity function y equals x. And I can see that it does follow my domain and range for the inverse function.